So in the last video, we saw how the system responds to the control input under varying conditions. And there's a bunch of different properties in the response of a control system to the varying inputs and how it behaves. There are two main kinds of response properties. There's the transient response properties and the steady state response properties. Transient response properties result from changes in either the set point or the conditions of the system as a whole. So if we get a gust of wind and we're driving down the road, that's going to affect our speed. If I change my set point, that is going to affect my speed too, and that's part of the transient. It's when things are changing. Steady state is after we've been, the system has sort of converged to a stable state, or it's just been running for a while. There hasn't been any changes in the input parameters of the system. That's what our steady state performance is. Transient parameters are things like the rise time. So here my set point has risen, and the rise time is how long before I cross that set point. So this is something I want to minimize. As I'm a process controller, I want to make sure that my rise time is as close to my set point as possible, because this is all error. All the error in here, this is all time when I am not on my set point, which is not great. Same thing here. This is something else. This is called overshoot. So overshoot is after a set point change, I miss my target and I have to come back. Again, this area under the curve between my actual measured process value and the set point is all error stuff. Right, so how much I've overshot is what my peak is as related to my what is the peak of my control variable, my process variable, related to my set point. So how far have I overshot as it's trying to converge? My settling time is how long before my process variable is inside of the bounds of that I set. I have some tolerance that I'm comfortable with. What is the tolerance that I have, and when do I get inside of that? So in this case, my settling time is about 105 seconds, something like that, and it takes a little while to settle into that range. Once I'm in there, this is our steady state, and this is where we live, so to speak, right? Our steady state error is after all of this stuff is converged, what's the difference between my process value and the set point? And you can see here, this is probably a proportional controller. It has a lot of ring and it takes a long time for it to settle down. There's a little bit of delay in action, then it overshoots, and then it takes a while to settle. Then there's the steady state error is pretty long. There's a pretty significant gap between where the system converges and where my set point is. So we measure damping as kind of how fast it converges, right? Overall, there's a complicated formula for actually measuring damping, but basically we want a system that doesn't oscillate, that damps down pretty quickly. So this is a system that oscillates a little bit, so it's not damped very well. An uncontrolled situation is something like this, where we start out, our process set point changes, and the system starts oscillating, and rather than those oscillations converging and damping down into a steady state, it starts to swing out of control, right? So this is an uncontrolled system, absolutely not what we want. An undamped system is something that oscillates forever at some natural frequency. So here, this is stable, it's not uncontrolled, it's oscillating all the time, and we found its natural frequency, and there's actually information in this that can be useful later on, because once we know our natural frequency, we know what the sort of base frequency of the system is, and we can play with some things later on. When we get to PID tuning in a later week, we'll talk about what we can do when we find the undamped condition. Underdamped is a situation like this, where we can see we start out oscillating and we oscillate for a really long time. Like we start out oscillating and we never really stop, even though the amount of oscillation starts to decrease. Overdamped is where we never oscillate. We actually take a really long time and may never actually reach our our target point. We now have an extremely long rise time, so it's too far. So this is an over damped condition. Critically damped is the sweet spot. This is where we get to our set point in a very quick amount of time. We have a very quick rise time. We try to minimize overshoot, and then it oscillates just a little bit and then comes back on target very, very quickly. This is where our settling time is minimally short, right? So an example we saw earlier was this is a underdamped system. So this one, it oscillates a little bit and it converges. So it's not perfect, but it could be better, right? So there's the various kinds of our response properties in control systems.